Hello students, welcome to this lecture on thermodynamics. In this lecture, we are going to discuss a very important topic in the thermodynamics chapter. We know that spontaneity of the reaction that depends on the total entropy change that we have discussed in our previous lecture, in the lecture number 9. And if we see, practically we will find that majority of the reactions and processes that are going to happen in the closed system or in the open system. And in the closed and open system, it has been accompanied with the enthalpy change or entropy change. And neither the decrease in the enthalpy or increase in the entropy will solely determine the spontaneity of the reactions. For this purpose, one new thermodynamic functions that we are going to define in this lecture, that is the Gibbs free energy functions. And we will understand these Gibbs free energy functions will solve this problem. That we do not need to do not need to consider at the same time, that is the enthalpy and the entropy. How that we are going to incorporate in this function, that we are going to discuss in this lecture. So in this lecture, the heading of the lectures, that is Gibbs free energy change and spontaneity. This is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. So, what is Gibbs free energy? First, let us understand. Gibbs free energy function is basically, you can write this, you can define it as Gibbs free energy is a quantity in thermodynamics, decrease of whose value is equal to the work done, equal to the useful and maximum work done, useful and maximum work done by the system. That will give you the, and it will be written like this, that is minus del G is equal to W maximum. Here G is the Gibbs free energy, Understand? So Gibbs free energy is mathematically being expressed by this equation H minus Ts. It is the Gibbs free energy function of Gibbs function. In this you can see that is H, T and S. As you know, H, the enthalpy, is a state function. This is a state function. This is also a state function, that is temperature, and the entropy also a state function. So naturally G will also be a state function, and it is a extensive property. G, we can say it is a extensive property. So what is more important thing, that is the change of the Gibbs free energy. Change of the Gibbs free energy can be calculated in this way. That is the basic equation, the Gibbs function, that is you can see this, and this energy you can write del H minus del T into S minus del S into del T. And at the isothermal process, when there is a del T is equal to 0, so we can nullify, we can cancel this term. So this equation will be reduced to this S, but this will del S into T. This is the Gibbs equation. This is also called the Gibbs equation. Gibbs equation. In this Gibbs equation, you can observe a very important thing, that here the energy term, that is enthalpy, is incorporated. Another term, this energy term is relates to the spontaneity of the reaction or process, and this term del S term is also related to the spontaneity of the reactions, that we have already discussed. And these two terms has been incorporated in this change in the free energy change, Gibbs free energy change, so that you can see for a single equation you can have both these terms. So by changing of this, you can able to easily say whether the process will be spontaneous or not. That is the main theme of this, that is the brainchild of this function. This function will help you about to ascertain about the spontaneity of the reaction without considering the enthalpy change or the enthalpy change. And it is built, this equation has been inbuilt, and here also you can see both these two important terms which contribute the spontaneity of the reaction. So we understand del G, that is the Gibbs free energy change, is equal to del H into minus del S into T. And if you see that this is an energy term and this is also an energy term, so naturally its dimension, the del G's dimension will also be energy term. So now we understand one basic thing, how del G is going to contribute, going to focus about the spontaneity of these reactions. Now we are going to discuss how del G is going to tell about the spontaneity of the reaction. For this we already know entropy change total is equal to entropy of the system plus entropy change of the surroundings. We already know. And when it will be greater than 0, then the reaction is spontaneous. Suppose the system is in chemical equilibrium with the surroundings. At that time, what is going to happen? The change in the enthalpy of the system will be, and the surrounding also influenced by this change of this enthalpy. If the system enthalpy is reduced, and same enthalpy will be gained by the surroundings. So we can write the change in the entropy of surroundings. Change in the surroundings, that is given by delta H by T. T is the temperature because it is in a thermal equilibrium. Thermal equilibrium means that it will have the spontaneous temperature. Del H, and you can write this with del in the system by T. This we can write because the heat is lost by the system and that will be gained by the surroundings. So we can write this del S total is equal to delta S system plus system delta S entropy change is given by this delta H system by T. So we can write this equation is like this: delta S total, this is very simple, that you can see T into delta S system and minus H, that is lost by this, divided by T. Now we know that this will be greater than 0. So we can, then only the system will be spontaneous. So we can write del S. Del S, we are not writing this system because all are become system. The del S system minus del H system, del H, the enthalpy system, that will be greater than 0. Okay. Now we can write delta H minus T into del S. We take the minus common with the bracket, that will be greater than 0. Now we know this is basically, what is this? This is basically the Gibbs free energy change, that is delta H, delta G, and it will be greater than 0, means delta G will be less than 0. So when the surroundings and the system having the entropy change greater than 0, at that time it will be spontaneous. In the same time, we will find that del G, that is the Gibbs free energy change, will be negative. At that time we will say this is a spontaneous reaction. So we can write the very important conclusion that when del G is less than 0, means reaction is spontaneous. Reaction is spontaneous. When, second thing, when del G is greater than 0, then system is non-spontaneous. We can write this non-spontaneous. Okay? And when delta G is equal to 0, the system is at equilibrium. System is at equilibrium. So we understand all the things, that how the delta G Gibbs free energy change going to influence, help us to predict the spontaneity of the reaction without taking care all the enthalpy and the entropy, because in the function itself this both the terms has been incorporated. Okay, so this is how the free energy change going to influence the reactions. So now what we are going to do, we are going to understand how the temperature is going to influence the spontaneity of the reaction. Now we are going to understand the influence of temperature on spontaneity. Influence of temperature T on spontaneity. On spontaneity. Spontaneity. For this, main function, that is G, is equal to H delta H minus T into delta S. The main function. On the basis of that, we will understand this. Suppose we make a table delta H, then delta S and delta G. When the enthalpy change is minus and entropy change is plus, at that time you will see del G is always minus. So we can write at all temperature, spontaneous. When the reaction have this specification, that is exothermic and its entropy change is plus, then at any temperature, at all temperature, you can see it is a spontaneous reaction. Just to reverse it, suppose enthalpy change is plus, entropy change is minus, negative. At that time, you can put this is plus and this is plus. So del G will be always plus, and at all temperature it will be non-spontaneous. Right? Now, suppose del enthalpy change is plus, matlab endothermic, and del S, the entropy change is also plus. At that time, what is going to happen? At that time, see this value, when it is plus, then this value T into del S is value of this will contribute the change of this. Change means the negative change of this delta H. So you will write this delta H. So negative change of this delta G will only have, in this case, when this value as the higher value, if the T is high, so when both del G and del H and del S, del H enthalpy change and del S entropy change, both are plus, then this will be minus, del G will be minus when this value T will be higher. So we can write at temperature high or higher temperature, you can write at high temperature spontaneous. For this case, for the endothermic reaction, you have to increase the temperature, then it will be spontaneous, right? If this is plus, both are plus, but at the low temperature, what is going to happen? Now this will be, the value will be plus. Then at low temperature, you can write at low temperature, the reaction is non-spontaneous. Okay. When both are minus, this minus and this minus, means it will be plus. So at that time, what we will find? That del G will be minus when this value is be low. So minus, del G will be minus at what temperature? At low temperature. At low temperature, this is spontaneous. And again, another case will be happen when at the high temperature, the reaction will be non-spontaneous. How it is non-spontaneous? Then you can easily understand that minus, this is plus and this is minus, and when this value will be higher, and it will outweigh this delta H, that is the enthalpy, and it will, the value of this del G will be plus. This is how the spontaneity of the reaction is depend on the temperature. Okay, I think that is understood, that you can able to understand. That's how this happened when the temperature is changing. We are going to discuss the change of the Gibbs free energy del G in the reversible reaction. In the reversible reaction. What will be the change in the Gibbs free energy? When the reaction is reversible, and at that time you can understand that there is a forward reaction also and the backward reaction also. How it is possible? It is only possible if the free energy of the equilibrium mixture is less than the reactant, free energy of the reactant and free energy of the product. At that time, every time you will find that delta G, both the cases, in both the forward direction or the backward direction, it will be negative. Then the reaction will proceed. So, at any stage of the reaction, we can correlate this delta G, that is Gibbs free energy, with the standard Gibbs free energy by this reaction. That is del G is equal to del G0 plus RT ln Q. Q is reaction quotient. What is this reaction quotient? That we have already discussed in our equilibrium chapter. That it is basically a ratio between the concentration of the product and the concentration of this at any time. So, when Q at the equilibrium, what is going to happen? At equilibrium, Q reaction quotient is equal to K, equilibrium constant. And at that time, delta G is equal to 0. So we can put these two values, we will get 0 is equal to delta G0 plus RT ln K. So now this value we can understand, we can rearrange this, we will find that RT ln K, that will be going to minus delta G. So from this we can able to calculate the equilibrium constant of this reaction, that is given by delta G0 by, this is ln K, delta G0 by RT, and K is equal to, you can get e to the power delta G0 by RT. Now, there is another thing that we can understand from this. This is RT ln K is equal to minus delta G0, and we know delta G is equal to delta H minus T into delta S. So, we can write this equation delta T minus delta H, and we can see ln K by RT. So we can comment on the K value. When K value is, when delta G is higher, means endothermic, delta H, that is a enthalpy, delta H, that is plus positive, means endothermic, highly endothermic. At that case, what is going to happen? The K value ln K will be less than 1. But when delta G is equal to the exothermic, at that time ln K is greater than 1, means K value will be less. Equilibrium constant will be less. Here, equilibrium constant for this exothermic reaction, equilibrium constant will be higher. And from this relation, we can able to understand this. So, we have understood the many aspects of the Gibbs free energy change. What is the relation between the Gibbs free energy change, and how do we say the how do the Gibbs speed energy with relates to the your spontaneity of the reaction, how it helps us in deciding the spontaneity of the reaction without taking care of this enthalpy change or entropy change. Okay. For the reaction, this is a reaction, gaseous reaction. The internal energy change is given by this, entropy change is given by this. You have to calculate the delta G, Gibbs free energy change. How do you calculate? First, you have to calculate, we know the delta G is equal to delta H minus T into delta S. You do not know what is this delta H, enthalpy change, but you know this and you know this. Delta H can be calculated from this equation. We know that is basically delta E, internal energy change, into Ng into RT. Ng is the change in the moles. See here, this is minus 5 kilocalorie plus change, that is Ng, that is the moles, number of moles of the product minus reactant. So here you can see 1 minus 2 into R is for this in terms of calorie it will be 2 and temperature is 298. So it will coming around minus 5 into, it will come in, if we calculate this, 2 into 298, that is it will almost minus 601 calorie. Okay, now we just straightforward put this in this relation, we will get that's delta G is 601 minus T 298 into delta S is given this minus 10, and it will be, you can calculate and you can get this value positive, this is plus. So this will be the answer. So this reaction is not spontaneous because delta G is plus. Delta G must be negative. Then this any reaction will be spontaneous. Okay. For a particular reversible reaction at temperature T, delta H and delta S were found to be positive. If the T is the temperature at equilibrium, the reaction shall be spontaneous when this option is given. We know reaction will be spontaneous at that time when delta G means that delta H into delta S will be less than 0. T is the temperature at the equilibrium means that delta H minus delta Ts is equal to 0 when this is T. So we can write this delta H is equal to Te into delta S. So this value, this delta G will be negative at that time when the delta T will be greater than T. At that time only this total expression will be negative. So the answer to this question will be D. The T will be greater than T when then the reaction will be spontaneous at that temperature, because at that temperature this del G will be negative because this value will be higher than this value, so it will make total term a negative. Okay. That is all for today's lecture. In this lecture, we have discussed a very important thing, that is the free energy change, that is the Gibbs free energy change, and we relate it with the spontaneity. Thank you very much for watching.